Can you guys see?
Yep, that looks good. All right, so now we have Chia-Hsien Shen talking about spinning binaries, effective theory, and hidden simplicity.
Okay, thank you very much. So first of all, I'd like to join other speakers and thank the organizers for the opportunity to speak, as well as organizing this wonderful conference. So today I'll talk about spinning binaries, EFT, and hidden simplicity. So this is based on the joint work with my fantastic collaborators, Zvi Byrne, Andreas Luna, Radu Raven, who just gave the talk, and Mao Zhen. So although this is based on the same paper with Radu, but the talk is designed to be orthogonal. So even if you miss his talk, they should be completely fine. Okay. So let me first go over again why are we interested in spin. So there's an obvious fundamental reason because in real world, black holes usually have spin. So for example, in this recent event reported by LIGO, this effective spin chi is 0.25. So this quantity is normalized between 0 to 1 for black holes. So you can see that this is not a small fraction. And because spin is a new degree of freedom, so it opens a portal into new interesting phenomenology. So for example, you can have precession, and that would lead to the waveform modulation. You can also use spin to test GR, as well as probing the internal structure for either black holes or neutron stars. But here I'd like to emphasize that there's also a very good theoretical reason why spin is interesting, because as you will see in my talk, that I should view spin as non-abelian generalization for the scalar case. So it's a little bit similar to the difference between QED and QCD. So even though QCD looks more complicated from the usual action point of view, but it's also the place where unsure amplitudes play a much powerful role. So I expect that to be the same, that spinning sector will be the place where there will be more opportunities for amplitudes. So there has been significant progress in recent years on spin, ranging from classical GR, EFT/NRGR, and of course for unsure amplitudes. So there are a lot of works, and I'm sorry I can't go over them. And we also have many interesting talks in this conference, and I look forward to the rest. The question is, what's new, and what do we expect to bring to this game? So although there has been a lot of nice results in scattering amplitudes, it's not obvious to us how these connect to EFT or the effective potential. So such connection is important because the effective potential is a straightforward way that we can apply the scattering amplitude results into bound orbits, which will be of interest to experiment like LIGO. And this is really a two-way communication because once you have that, then you can import the results in GR, for example, EOB, Salesforce, AD, and Hamiltonian, and seek for insights to amplitudes. So that will be the first part of the talk. So in the second part, I'll try to use the development in the first part and sharpen the understanding between amplitudes and divert observables in GR, at least in the scattering event. Okay. So let me begin with an inverse question. So the question is, suppose someone just hands you a classical spinning Hamiltonian, a two-body potential. The question is, how would you calculate the corresponding amplitude? So because this is a two-body potential, the corresponding amplitude is a 4-point amplitude, a 2-to-2 interaction. So for convenience, let me consider in the center mass frame. So I have particle 1 and 2. The three momenta is P and minus P. And the momentum transfer here is Q. So in terms of this 3D three momentum, the kinematics is controlled by P squared, which plays the role like S in the usual covariant kinematics. And Q squared is literally minus T. And for onshore condition, we also have P dot Q is given by half Q squared. And this relation will be crucial afterwards. So for linear order in G, or tree level interaction, this is really straightforward. Because what we expect in the full theory in gravity is that this 2-to-2 interaction is given by this T-channel graviton exchange. But since we're in the EFT, so this has been integrated out, so we only have these 4-point vertex. So to get from potential to amplitude, it's really straightforward. Now you just take a Fourier transform from the real space potential, and then you place the kinematics on shell, and then you're done. So this is the usual way we learn in Pascal, for example. So the only remark I want to make here is that there are many different versions of spin, actually. And so the version you have in the amplitude depends on what spin you use in your potential. So throughout this talk, I'll use the so-called canonical potential with canonical spin. So this canonical spin that have this standard Poisson bracket. And you can think of this as a spin boost back to the rest frame, which is three-dimensional and is related to the usual covariance spin through this formula. But the question is, can we guess what type of answer we expect based on some simple principle? So an important limit we want to take is a classical limit, which means the macroscopic angular momentum, L or S, the orbital and the spin, they are much larger than h bar, which is set to 1 as usual. So L is related to mr. R is the two-body distance or the orbital size of this binary system, which is 1 over q in momentum space. So in turn, that means the kinematics is nearly forward in classical limit. So m or p is much greater than q. So the relevant expansion we can take under classical limit is the so-called spin expansion. So it's a ratio between S over L, which can be written as S over R or Q times S in momentum space. So now we can simply write down the interactions that we expect. So whenever we have 1 power for S, we must come with a 1 power of Q. So for linear order, this is the standard spin-orbit interaction. And we have these 5 different type of choices we can have for quadratic order in spin. However, we still want to pay the kinematics be on shell. And as I said before, on shell already set this k dot q into q squared. That means these two operators, they're all proportional to k dot q. Although it looks like classical in the beginning, but once you place these on-shell kinematics, you find out that these are quantum mechanical or redundant. So in the EFT language, we call this, we can move these operators by using equations of motion. And this is a very general argument that's valid for any order in G. So it's very analogous to the isotropic gauge in the spinless case. But here you can see it's even more powerful in the spinning sector, because not only you can constrain the type of coefficient you have, you can also eliminate these operators. And we also have several nice talks on standard model EFT, where you can also apply similar on-shell methods. And you can refine this statement at order G, as shown in this paper by Chong, Kim, Huang, and Li. And let me go over them. So a spatial case at order G or tree level is that these two operators are proportional to q squared. That means it will completely cancel the graviton pole. And in real space, that means the corresponding potential is a delta function, which is not long range. That means you can simply ignore these two operators at tree level. And that's the argument that's being introduced in this paper by Yuting and his collaborators. So at tree level, we only expect these two operators up to quadratic order in spin. And you can easily generalize this to higher spin order simply given by same building blocks. However, I want to emphasize that these two operators, they become important once you're beyond tree level, because this q squared doesn't cancel with the graviton pole, and we still have a long range potential coming from these two operators. So you can see here that the argument is very straightforward. It's basically a one-line argument coming from classical counting combined with on-shell computation. But it's hardly non-trivial if you compare with some standard potential. So for example, shown by this paper by Yuting and company that involve hardly non-trivial canonical transformation, that these agree with the standard potential. But here we can even generalize to higher order in G. So for order G, linear order in G, we only expect these two terms for linear and quadratic order in spin. So now let us take the answer in GR. This is taking the potential from theta from GR, the next to next leading order. So we plug into this potential and we'll find out these two function. So in this R results in Pn, so it's written in terms of velocity expansion. And that fully agrees with the higher spin result that Badu talked about. And of course, the higher spin series result is relativistic, so we can complete this velocity expansion series. Okay, so so far it has been quite straightforward. It's almost like a textbook as in Pascal. So now let's consider order G squared. So for order G squared, as usual, we know these are relevant diagrams in the full series. We have the usual triangles, the boxes. So in the EFT language, this triangle, they more or less correspond to this order G squared vertex. For these boxes, it corresponds to this iteration diagram in EFT. You can see that once you blow up this contact vertex into a graphite exchange. So by now we know that these they contain classical relevant information, and that's the thing we need to include at order G squared. But now we found out that we run into an obvious problem. The question is, how do we treat classical spin? And moreover, what is the propagator? So for example, in the case of fermion, we know we have P slash in the numerator. So the question is, what do we want to put here? So really what we want to do here is want to combine the spinless post-Minkowski and EFT by Chong, Rustin, and Salon, and some earlier works on spin, for example, this actually very important paper by Vadia, and earlier work on NRQED and QCD. Okay, so there are two obvious choices how we treat classical spin. So the first one is, as usual, as in textbook, any classical quantity should be viewed as a classical C number. So the second choice is that we should just commit to doing quantum theory, and the classical spin we should just treat as the operator. So now in our language, the commutator, the spin commutator with spin is linear order in spin. So the usual argument why classical objects are C number is because the right-hand side has an H bar, and therefore the commutator is suppressed, and you can treat it as a C number. So here in classical limit, we view spin to be large. So here this is suppressed in the sense that it turned S squared into S, so therefore it's suppressed. However, remember that because in classical limit, the kinematics is nearly forward. So these propagators, they're highly enhanced. So therefore, we find absolutely no reason that we can drop this commutator once we beyond the linear order in G. So the statement in our work is classical spin is indeed non-abelian, and you should treat it honestly as a non-abelian operator, which means it satisfies the usual the usual SO3 rotation algebra. So from hindsight, there's nothing really weird about this statement, because even in the level of classical equations of motion, the spin that satisfies this canonical Poisson bracket. So the role of this SO3 algebra is really to reflect that the spin have this time evolution, the Poisson brackets. So just like now we all know that loops contain classical, we can upgrade this statement, and the commutators of spin, they also contain classical pieces. So the correct way we should view amplitude is that it's a transition matrix between initial and final state, and it's a matrix value with the data group of initial and final state for this initial and final states. So when we say spin, what it really means is the SO3 rotation structure of this transition matrix. And that's also solve another problem because the propagator numerator, by definition, is the state sum. And because we're in the data group, so the state sum is trivially just identity. So you might worry about this proposal because when you promote a C number into operator, you will have ordering ambiguity. So the statement here is that although you have ambiguity in the intermediate step, but when you compute the classical relevant quantities in the end, for example, the triangle coefficient or the classical potential, those objects should be free from this quantum ambiguity. Okay, So now, once you realize on this conceptual leap, the rest of the calculation is straightforward. So for order G squared, we have these two diagrams. So this V hat is the vertex from your classical potential. So the only difference is that this V hat you should treat as operator, and the ordering matters. And whenever you see spin for this 1D diagram, you should organize that into the ERAPs of SO3 representation. So it's very similar to how we should reduce the range generators that Batu talked about. And here we see explicitly that this commutator will arise. So let me not go over the details, but let me just highlight some qualitative new part for the spinning sector. So first, let me consider the spin orbit interaction. So in the spin orbit, we see this 1 over p squared singularity. So this is the same as 1 over sigma squared minus 1 that Batu mentioned. So you can see here, this is coming literally from this S channel cut because these are nearly forward. And the residue is fully dictated by the earlier order. So once you do the matching, the rest of the term is completely local. And in the scalar case, because the tree level, it only has a trivial numerator. So the iteration stays as a box. It doesn't have a triangle contribution. So therefore, we don't have this singularity in this scalar case. And for spin 1, spin 2, the new feature is that this commutator effect I talked about, that's the first time that this happens. So here, this combination is the spin orbit coupling times spin 1, spin 2 in these two vertices. So overall, we can count that there are 3 spins in total. However, it still contributes to the spin 1, spin 2 amplitude, precisely because the commutator reduced 1 power of spin. Okay, so now we can plug in the state of GR. So these are the state of next to next leading order posed in the PN Hamiltonian. So we can plug in this Hamiltonian and generate this gauge invariant amplitude in the velocity expansion, which fully agree with the higher spin theory that Batu talked about when we expand in velocity. We can also compare with other data, for example, EOB and probe limit, which are both of them order in velocity. So this entire thing serves a non-trivial track, not only for the EFT formalism I introduced here, but also the higher spin theory that Batu talked about. So combine all this, we write a new result in GR, which is the spin 1, spin 2 potential by matching to the amplitude. So the relevant potential, we have 3 terms here. So for each of them, you can do the usual expansion in velocity or in G. So in this work, we have the new order G squared piece, and we have cross-check with next to next leading order in GR. Very good. So now we have this connection established, and we can try to understand whether we can sharpen the connection between amplitudes and observables in GR, at least for scattering. So again, let me begin with the question. So the question is, do amplitudes encode all classical observable in the scattering event? So this is a question asked by these 2 beautiful papers from Kasawa, maybe Eikonal, and the spin extension with Vines. So here, let me just focus on the conservative sector. So for example, in the central mass frame, I have an incoming particle P with an impaired parameter P, and we want to measure what's the final state momentum for spin 1 and spin 2. So without spin, this scattering only happens on a plane. For example, here, it only happens on the XZ plane. But once you turn on spin, it becomes more complicated, and this is really a 3-dimensional motion. So I want to ask the same question as these authors did, but in a slightly different context, the so-called Eikonal Phase formalism. So this is a natural formalism for a conservative sector, at least, because the S matrix, at least in the impaired parameter space, so S matrix is unitary, and the impaired parameter space is Bernoulli. So it's easier to talk about this phase. You can see more detailed construction from Julio's talk later today. So it's very popular because it gives you a very efficient way to extract physical observables from amplitude. So for example, in the spinless case, the only observable is the change in angle, which is given by the derivative with respect to the Eikonal phase. So the question is, can we generalize this for the spinning case? Namely, we want to find some function which give you the change in momentum, spin 1 and spin 2. So you might against this idea, because remember, all these are 3 vectors. So even after you use all the conservation laws, you still have 6 variables. So the fact that if it can come from a single phase, it sounds a little bit too good to be true, compared to a scalar case where you have 1 angle from 1 phase. So that sounds more feasible. However, it's not really the first time in physics that we have some master generating function that give all the observables in the same time. For example, the partition function in QFT, or in thermodynamics, they can get endpoint function or the thermodynamic pressure, entropy, etc., by taking appropriate derivatives. And on the other hand, we also backed by this amplitude formalism from these 2 papers, not only as like mental support, but also give us some hint about how do we find this concrete function. So the first part I talk about is very useful because on one hand, we can calculate these observables from classical equation of motion. And on the other hand, we also have amplitudes available, which will give us this Eikonal phase chi. So the question is, how do we search such functions? So for linear order in G, the answer turned out to be quite straightforward because at this order, you can treat the trajectory as a straight line or like the standard Wilson line. So the answer is given by this simple commutator. So any change in this observable is given by some commutator with a corresponding operator. So Eikonal phase is simply given by the Fourier transform to the impaired parameter space. So the 2 observables we can get is the change in momentum along the transverse direction compared to the incoming direction. So the corresponding operator is literally gradient B. And here you have to treat B as a 2-dimensional vector. And the change in spin is literally given by the same associative algebra, taking the spin operator. So once you can get directly is the change in momentum along the incoming direction, but this is constrained by the energy conservation. So even in the spinless case, that's also the case. So we can prove this, which is simply because the amplitude at this order is proportional to potential. So now we just have to plug in this to equation of motion, and then you can verify this formula. But there are many things that will be different at order G squared. For example, you can't treat this as a straight line anymore. And also on the amplitude is not directly related to potential for order G squared. So we compute the answer in equations of motion, and that's the answer we found in the beginning. So these first 2 pages are for delta P, this one is for delta S, and this depends on the input Hamiltonian, so it looks quite complicated. So the question is, how do we organize this thing? So it turned out that once we stir this long enough, it condenses into one line formula. So at order G squared, the observable is given by this result in terms of Eikonal phase chi. So first term has exactly the same structure as order G. So the Eikonal phase chi 1 is the same as before. For chi 2 is given by the 1 loop triangle part. And we have these 3 additional terms, which is depending on the quadratic order of the 3-level Eikonal phase. So this one is a double commutator. And these 2 has a mysterious DSL function, which is a derivative with respect to spin and orbital angular momentum L. So this formula, especially the first 2 terms, is particularly enticing. So we try to rewrite the rest of this combined to this term by defining this variable, this operator D, which is basically identity plus this DSL function. So once we do that, we make an order conjecture, which is if Eikonal phase is given by chi 1, chi 2 plus higher order, the observable is given by this commutator O with this exponentiating factor with this D operator and with this inverse factor. So again, this is a conjecture. We have proof for order G for general spin interactions. For order G squared, we have evidence up to spin 1, spin 2. So that brings to a perfect place for summary. The most important conceptual part is that classical spin should be viewed as non-abelian operator, and therefore commutator matters. So in the first part, I constructed an EFT for spinning binary. So the EFT is important because that's a straightforward way to apply to bound orbits, which will be of interest to LIGO and Virgo. And along the line of constructing this EFT, we are guided by unsure simplicity. For example, we have a minimal basis of operator, and we use gauge invariant amplitudes to compare different answers. And I actually said that this EFT is valid for higher order in G and spin, although I only talk about order G squared amplitude spin 1, spin 2. So in the second part, I talk about spinning Eikonal formula. So it's quite striking to us. So the question is, who ordered this? And we don't really have a good answer, but maybe this paper by maybe O'Connor and Vines could help us. And also the Eikonal formula here is only valid for scattering. So important question is, can we lift this into bound orbits? And this work by Gregory Carlin and Rafael Porto, the analytic continuation might be very useful, again, in this case. And last but not least, of course, it was a bit aggressive to resolve something with only order G and G squared. So we definitely need higher orders. And that's something we're thinking about. So with that, thank you.
All right, thank you, Chia-Hsien. Let's have another virtual round of applause. And open the floor to questions. While waiting for that, is there an intuition that you have for this operator that you define, this mathcal D, that you have to compactify? I mean, other than post facto knowing it's the right thing to do, I mean, is there some physics there?
So I'm not sure, but maybe it corresponds to some, I'm not sure. Yeah, but maybe it corresponds to some, you have to change your state, rotate your state in some way. Or maybe that's why, but I'm not sure. It's quite mysterious to us.
Okay.
I think
Looks like
so actually, can I ask you a question? I for some reason I can't raise my hand. I think because I'm a co-host.
Yeah.
But I think we all have the same problem. But my question was, so Josh, and of course you know that you recall that in our two-loop spinless case paper, we found this pattern that the EFT amplitude, which was IR subtracted, was precisely p squared, which later became and was proven as the impetus formula by Porto and the NBI group. So do you find the same pattern here? Do you find the same structure for the spinning case?
Obvious. So one thing is that the impetus formula ultimately is gauge dependent because it's the piece of R which depends on your coordinate. So we think the more appropriate language is the Eikonal formula because in the spinless case, we also have the standard very nice Eikonal formula. And also we look into the impetus formula, but we don't find anything like obvious in the spinning case.
I see. So basically you're saying you can change gauges in some sense, so that it's not like well-defined to try to compare this to
We haven't gotten that far, but just even look at the finite part of the 1D amplitude and the piece of R, we don't find anything obvious.
I see. Okay, thank you.
Looks like there's a question from Rafael Porto.
Okay, Cliff, you stole part of my question. I was going to ask if you checked this because we show that the spinning case also works for aligned spins.
Yes.
That the analytic continuation works. You have to analytically continue in both the canonical angular momentum and the spin, and then you can switch between the scattering angle and say the periastrum advance, for example. And for this to work, something like impetus for the aligned spin case has to work. And I was going to ask you whether you check if you take the final part of your amplitude that you isolated, and you check that gives you the p-square from which you can read the coefficients of the scattering angle that Gregor and I gave to all PM orders. Does that work? Check this.
At least for generic spin, it's not obvious.
But for align spin, this should be straightforward for you to check.
True. That, yeah. Okay, yeah. We're thinking about that. Thanks.
But you understand the question, meaning if you take the line spin and you take the FNs, you should check whether that gives you the angle.
I think that probably the answer is maybe 99% yes, as you said,
Okay.
because once you take a line spin, everything degenerates with the scalar case. So spin
Exactly.
is a number. So yeah, the answer is probably 99% yes.
But that gives you a formula which is much easier than the one that you wrote, because then you know how to relate directly the scattering angle to the delta P.
So I should say here in this formula, it's crucial that the non-abelian natural spin is important, because if the chi is if chi were abelian, then you just take a derivative and then you get back to the standard Eikonal formula. So the exponential fully cancels because those are just number. But if they were not abelian, you cannot do that. And for example, this double commutator is important. In the align spin case, all these drop out, and you just
you evaluate them before taking the commutators.
Yes.
I see. I see. So then it's just d chi dv, you get the scattering angle even for a line spin.
Exactly.
I see. Cool. Then impetus work, Cliff, for a line spin.
Yes.
Cool. Thanks for the clarification.
So we have another question from Ben Maybe.
Hey, Chia-Hsien.
Hello.
You may have just indirectly answered this, but could you say a little bit more about how the orbital angular momentum appeared at order g squared?
So yeah. So here, just view this as a change of variable from the impact parameter. So L is B cross P, and that's literally what we mean. L here is incoming L, the original L.
Yeah.
Just like the S is the original S.
But so do you still have anything from it in the align spin case?
No, that's no, because you need the epsilon ijk. So in the align spin case, everything's aligned, so this leverage theta kills everything.
Okay, great. Thank you.
Sure.
And then Justin has a question.
Yeah, this is maybe getting a bit redundant now, but just to clarify, in the slide that we're looking at right now,
Okay.
the last three terms,
Yes.
They all three vanish for the align spin case.
Indeed.
Okay. Okay, that's it. Thanks.
Yeah, so it seems probably easier if you look at this order formula. So in the align spin case, this capital D is just identity. And the chi here is ordinary number. So it's abelian. So in that case, the only operator you have is a gradient B. So you just hit it with the usual derivative. And the chi just exponential just cancel because they are purely numbers.
Okay, got it.
Then you get back to your standard formula.
Thanks.
All right, so let's thank Chia-Hsien again. And we will reconvene in 25 minutes, whatever time that is for you in your local time zone. Until then, this could be your new lunch break. Thanks, Chia-Hsien.
Thanks, Andrew.